Okay, thermal expansion. We have a alpha, which is known as the thermal expansion coefficient. We can use the equation the change in length equals the beginning length multiplied by alpha times the change in temperature. Okay, now how does this work? Well, we will have a beginning length of this bar here. We'll call that length naught. Alpha will be a known value looked up in the table or provided on the test. And then you can plug this in with the temperature change and get the change in length. If we want the final length, you will add this to the beginning length of the bar. Now what about gamma? Gamma is the area expansion. That is going to equal 2 times alpha. Now let's take a look at this. We can calculate the expansion of this side, the area of it, or this area here as well. We can call that the beginning area A naught for this side here. Now why is it 2 times alpha? Well, we have a length that might be expanding and a height that's expanding. So there are two things expanding. So then we can say the change in area is equal to the beginning area multiplied by gamma times the change in temperature. Now we can also have beta. Beta is the volume expansion coefficient. It's going to equal 3 times alpha. Why? Because we have a length that's going longer, a width, and a height. So if I want to know the beginning or the final volume of this, I will then go the change in volume is going to equal the beginning volume times beta times the change in temperature. Okay, the next question here, what about the calorimetry and latent heat? If we put ice into liquid water, we have two things going on. The first item is we have to melt the ice. So the heat flow there is all related to melting the ice. So Q is going to equal then the latent heat multiplied by the mass. So the latent heat could be in joules per gram or joules per kilogram. That would be the L value. And then mass must be an equivalency. So we have 25 grams here. We'll multiply 25 times the latent heat for ice for joule per gram. Now once the ice is in there, it all melts. Our next equation is really for calorimetry. Q is equal to specific heat times mass times the change in temperature. Once the ice melts, it'll be at 0 degrees Celsius here. But the surrounding water may still be at like 25 degrees Celsius. So then they will need to, heat will flow from the warmer water into the cooler water until both are the same temperature. So the change in temperature, okay, will be guaranteed to occur because of the fact that the zeroth law of thermodynamics applies. Warm will flow into something that's cooler until they're both the same temperature.
Let's get physical.
Our next example here is what about a sample of a gas? Okay, the sample of the gas here, okay, is going to have average velocity associated with it. It's also going to have kinetic energy associated with it. Okay, so if we want the velocity, root mean square average, that's going to equal the square root of 3 times r times t divided by m. M is going to be the molar mass of the gas. Okay, and R is going to be the 8.31 and T is the temperature. Okay, now the temperature for that, remember, is a measure of average kinetic energy of something. So we use this equation if we're using molar mass. Now what about the kinetic energy of one individual atom in that gas? Then we'll use the equation 3/2. And then we'll multiply this by Kb, the Boltzmann constant, and multiplied by the temperature of the gas. Now the Boltzmann constant, the 1.38 times 10 to the minus 23, is in joule over kilogram Kelvin. So we only use this when we're interested in knowing what the kinetic energy of an individual atom is. That's when you use the Boltzmann constant. If we're interested in using molar mass, then we use this equation here. And then finally, what about the internal energy of a gas? U is going to equal N. So again, U is equal to N 3/2 R times T. Okay, this is for the internal energy of a gas. Now this is a monatomic gas. If it was a diatomic gas, then it would be U equals N 5 halves R times T.